So is this on? Is this on enough? Okay. Did I press the right thing? Okay. So this was work done with Ian when he was postdoc over at NIST. It turned out my division chief actually dropped him in my office. And it turned out that he knew something about simulation tools, and I knew something about SysML and UML-based modeling. And so we got to talking, and then this was the result. We did this work on the integration. So this is the structure of it. The motivation approach has a lot of SysML introduction. I don't know if that's necessary here. We can see. And then we go on and do this simulation overview for those folks who don't know so much about the simulators. Then talk about the extensions and go through an example and show how you translate into the simulation file formats. So model-based systems engineering, I'm sure you all know, it's basically trying to codify this process where we're starting with user requirements and working your way through high-level designs to lower-level designs and doing the analysis and testing and ending up with a design that you can actually send off to the factory. This is just sort of a cartoon of that. Modeling languages, at least as OMG defines them, tend to be graphical, but not necessarily. They could be textual, that have various graphical model elements. They're assigned terms from the specific domain, like in SysML, the requirements and so on. And then they have what's called the semantics, which is what's going to result from drawing this picture in the actual product or the factory that you're designing. SysML, the systems modeling language, was initiated by INCOSE, which is the primary group of system engineers, professional system engineers. And they coordinated, they'd been working on modeling language for quite some time, and they coordinated with the OMG, who they recognized as being a central group in that. And so at OMG, they issued an RFI and an RFP and developed SysML in the first half of the 2000s. And I don't know how much we have to introduce this. You might have seen this. They have diagrams specifically for requirements for the components of the system and how they're related. Also how they behave. There's 3 kinds of behavior models. And also parametrics, which are basically the way that you express equations and constraints on it. SysML extends what's called the unified modeling language, which is pretty much the de facto standard modeling language among software engineers who use modeling languages. And INCOSE chose to extend UML primarily because it was a popular language that they saw that it would help them. They thought that it would help them to deal with the fact that modern systems have so much software in them. And if their reasoning was that if they piggybacked off this, they'd have better integration between the software engineers and the others. So when you look at the SysML diagrams, you'll see they're derived from the UML versions. You have your structural ones that go into the block definitions, which are basically your system components, the internal block diagram, which is how they're connected together, and so on. And all of them are derived from the UML diagrams. Some of them are exactly the same. The behavior diagrams especially have not been particularly extended, but they're all available in SysML. So I'm pretty sure I stole this from one of John's slides. There's an idea that SysML could be used as a hub for all the activities of engineering, because this is basically what system engineers do. They are the people that are in between the folks who have the requirements, the customers, and the discipline-specific engineers who work on hydraulics, electronics, and so on. So they tend to be the folks who have to coordinate the whole projects. In fact, when you go to INCOSE, there'll be tracks on project management. So there's an idea that it made sense that SysML could act as a hub for all the tools that engineers use, and it wouldn't replace them, of course, but it would help coordinate their use. And this talk is specifically about the solver-based simulation tools. Solver-based simulators have a lot of interfaces. They look like modeling tools, but actually underneath there, these diagrams, which are domain-specific, for example, for electronics or signal processing, actually translate to equations, differential equations. So they aren't like modeling tools in the OMG sense that they capture the domain specifics, because it's all translated to equations. And then the advantage of them, of course, is that when you run them, you can find out how these variables, all these numeric variables, change over time, given the structure of the system that you drew out. So if you look at the solver-based simulators, they have all these interfaces, but this looks like the same slide. Which way did I go? OK, so the idea was, well, these simulators, because they are essentially, even though they have many domains, they have the same underlying mathematics. The idea was, well, maybe you could use SysML as a hub for these. But rather than do a point-to-point from SysML to each one of these, it seemed to make sense, and this is what Ian and I pursued, is there something in common between all these simulation languages that could be taken as an abstraction of them? And then any integration you had to do with any individual one would be smaller. You could reuse this common abstraction. So that's the general idea, is what I'll be presenting today, is this extension of SysML that captures what's in common between these various solver-based simulators. So to understand what that is, actually, we have to review these simulators and what they do. And like I said, since all of these different domains, whether they're hydraulics or powertrains or the specific notation that looks domain-specific to the engineer, actually the simulation tool underneath, it's all the same algorithms because it's all the same equations. And the reason they can get away with this is because it turns out that the underlying physics has this commonality to it, which could be loosely described as flowing substances of some sort that are being pushed with a certain pressure, you might imagine, against a certain resistance, and that have a certain flow rate. And this abstraction, which I guess was arrived at by the late 1800s, is quite powerful, because these things, which look very different, electricity, even momentum can be considered something that's flowing, hydraulics, heat energy, and so on. It turns out that the equations are all the same. So because of that, just to give you an idea what these are, if you imagine whatever the substance is that's flowing, which could be quite very abstract, like momentum, or it could be a charge or so on, there's a flow rate that it's going in when it's moving between components. There's a flow rate as it goes into what you might call an abstract channel or pipe. And there's flow rates that come out. And the potential, which is the word for, say, how hard it's pushed, like the voltage or the pressure, it remains the same on all sides. And you can imagine this: if you got a pipe full of water and you put pressure on one end, you're going to feel that same pressure on the other ends, no matter how many ends there are. But the flow rate, however, has to add up. If you have a flow rate, a certain volume of this substance moving through on one end, it has to add up on all the other ends. And there are different names for this law in each of the domains. Kirchhoff's, I can't even remember them all. Some of them are French, I can't pronounce them. But they all have the same form. And you also have to account for the fact that the flow rate isn't always in one direction. Sometimes there's a pushing back that causes the actual balance to be that the flow comes the other direction. So in general, your flows are going to go in both directions. Not always, but they can go in both directions. But the rules still hold. It's just they treat flow backwards as a negative value. And it turns out it's actually very useful for information flow, which is like such as signal processing, that you can use the fact that the potential is the same on all these ends to simulate information, because information, when you send it, it can be copied, like voltage. When you send it, there's the same voltage in all the downstream pins. And that way, you can treat information as potential. And that's what a lot of these tools do, actually. They omit flow rate and just deal with potential because they know that at the other end, the values will all be the same.
What do you do with geometry?
Well, these simulators actually only work on numeric values, individual.
Allowance.
No, but that's important, right?
Yeah. But it was not the goal is just to focus on specific.
No, I understand, but I mean that's one of the things you're struggling with, because that is fine. You can do that. You can even do Hamiltonian force, but you need to put geometry. Now, can you do it by defining the boundary conditions for the various equations? Or no?
It depends how powerful is the tool that you're working.
Boy, I need an answer.
Now, no.
Thank you.
No.
And geometry is a pretty complex, although it's numerical, it's a very complex.
We need it because the main difference between the cyber and the physical is that the physical has matter. You need matter description, you need geometry. So this analogy is okay up to a point.
Yeah, when I say information here, actually, within these simulators, they have a very narrow view of that. What they mean is a numeric signal, a value, which is just a voltage. So it's a bit misleading for me to put information there. It's in the most narrow sense. It's like
you can. There is something that's called generalized networks and Hamiltonian force and all that stuff, which unifies all that. But even that framework misses geometry. So if you're going to...
So they saw, I know that they may have, in all the tools, they try to, if you have a component which has geometry, they can pass from this to a lump description.
Of the...
Yeah. So you can get something like Modelica with some parameters.
So, how does Modelica do?
Modelica doesn't do. You just, the way they
You agree with that? I'm looking at you. Left corner.
I mean, geometry is linked.
How do you model geometry? Model?
It's linked to the physical properties.
But you can input geometry, right?
It's embedded in the equation.
You can input
It's
geometry.
parameterized.
It's parameterized in the
Because you
equation.
have the boundary, not in the equation, it's the boundary condition, yeah.
Huh?
It's not so in the equation, it's the boundary condition.
I don't think that they work with boundary conditions.
How are you going to model the thermal analysis of an engine of a car in Modelica? If you take into consideration the geometry of the various constructs you put in the engine to help you in the heat dissipation. How are you going to do that? And your object of your design is to change different geometries of heat dissipation so that you have a better efficiency. Can you do that or not? I don't think so.
No, you can't.
Right, okay, sorry.
So continuing here.
Because we ran into the same problem with Leonard. We're looking at bond graphs, right? Because bond graphs is something that's related to this. But we don't have to geometry.
Because there is a generalized Hamiltonian form.
Yeah, all of these things can put in generalized Hamiltonian form, the same format as Modelica. Yeah. But that's useful because now you have eliminated the new parameter model. Because then you have a Hamiltonian form for the
Conservation law, that's all what we need.
you have a formula in the book, so that's very useful. Okay, sorry.
So this is a bit of detail, but it's important when you're looking at picking the simulators. The rates of flow, if you have unidirectional flows, the way these simulators work is you can only model the potential. That is, if you're including the flow rate, you have to assume that the flows could come backwards. That's just a constraint in the way they work. And also, they don't allow unidirectional flows to be merged. These are kind of minor things, but when you get into actually using them, you find out these sort of two classes of problem, whether you're dealing with potential or whether you're dealing with potential and flow, and they're just different. So let's look at this extension. the overlap here is that the system engineers are concerned with picking the components, and in particular the kinds of interactions that will happen between the components and so on. And this involves picking the kinds of things that are flowing between the components. And at that point, that helps them direct to, well, what kind of engineers am I going to need on this project and so on, or which engineers do I have? It may decide how the interactions are going to be defined. So they will be concerned with the kind of thing that's flowing between the components, whether it's charge or heat and so on. And as I said, with the dynamic simulators, they actually abstract from that. The simulators aren't concerned with the kind of thing that's flowing. However, both are concerned with the direction of flow, in particular if it's unidirectional, in which direction that is, or if it's bidirectional. And so you will find that the simulators...
Why do you say systems engineers aren't concerned with the force? Right? I mean, why would a system engineer not be concerned with force?
Well, by the time you get to here, you've picked a mechanical engineer that you've farmed that kind of thing out to. You have to, the system engineer is not a discipline engineer. That is, they don't tend to be experts in mechanical or electrical or so on.
Because the force is not the real object in good physics. Right?
Yeah, but I may have requirements that...
Yeah, but if you learn good physics, you never talk about force. But they're all subject.
Okay.
It's not so much related to that. The derived requirements may come down to here, but by then you've involved the mechanical engineer.
Sure. Okay, that's fine.
So I wouldn't say they're not involved with it, but their primary concern is to identify the engineers involved and the kind of generally the kind of thing that's flowing between components. So
They define domain.
yeah, they need to define the domains.
You know how many domain experts they need. Or in the other side, how many domain-specific languages they have to deal with. That's the real practical question. The chemical domain language, mechanical, civil, structural, what? The system engineer, you need to know that. Sure. Even if you just take your software. Because it's not going to be just Java and C, right? It's going to be like, because the domain experts will come with his own tools, their own tools. And they're not going to change that because you tell them so. So they would like to be able to cook with something. That's the question they're addressing.
So, but as I mentioned, the dynamic simulators are concerned with the direction that these substances are flowing, even though they don't care what kind it is. And the system engineers are also concerned with that, and SysML is a way to represent that. So the general idea around this extension was the hook is the direction of flow. That's the overlap in which we can hook up the extension into SysML. So the way SysML specifies the kind of thing is flowing is something called a flow property, which these properties, that word property in engineering sometimes just means numeric, but in UML and SysML, it can be any kind of thing.
Perhaps it's important to mention that there were some changes with the flow property from the newer version of SysML brought some changes compared to older.
Yeah, the flow properties themselves didn't change, but the way they were wrapped in the ports changed. So the focus now is, well, the focus of this, unless you get into the discussion of ports, you're okay with flow properties, because they just, these properties tell you what kind of thing is flowing, and then when the system's actually functioning, their value is a quantum or whatever infinitesimal slice of the thing that's flowing at that point. So this is the way that SysML will tell you what's flowing, and then you can annotate with the direction, like this is in or out. And so this is how SysML represents the kind of thing flowing in that direction.
Because we can think in terms of ports, but in terms of structure and behavior. Correct?
Well, in SysML, all the ports are structural. And that was actually one of the changes Ian's talking about.
We have a behavioral theory, which you do right? It says that a single very dynamic, there's a port. And
Right.
as a matter of fact, it goes beyond that. It says which part of the port I will consider as inputs and which part of the port I will consider as outputs is a matter of design.
Right.
They call them modules.
Right. And let me clarify. The word that what we're doing now actually is traversing between two languages, and the word port is especially problematic because it has different meanings in each of them.
Is not. It's because in control theory, right, 20, 25 years ago, a very famous control theorist from John Williams said, wait a minute, we have to think about dynamics as ports, where, and I give you a very simple example. You take an electrical network and it's dynamics. Let's say you write in MATLAB. You have millions of options about what you're going to call input ports and output ports.
Yeah, I'm getting.
It's subject to design. It has to do
Yes.
about how you split the dynamics and
Yeah.
how you hook.
I'm getting to that, but my primary point I want to make is that the letters P, O, R, T, when put next to each other, have different meanings in different linguistic communities. And one of the difficult things Ian and I had is that there is more than just that word, but a number of words like connectors and so on, that when you traverse these two communities, and especially when you get into the particular simulators, there's all this punning going on. There's all these words that are the same but mean different things, or are different and mean the same thing. And that's part of the work actually that Ian and I had to do, is to sort out that kind of mapping. Here in SysML, the ports are considered structural, especially in this new version of SysML that Ian's referring to. And then you put the behavior on those structural elements. One of the ways you can do that is with the flow properties. It tells you something about the way things are flowing through this port. So the port is something through which things flow. It itself is a structural element. So like on a car, you see that place where you put the, you go to the gas station, there's a little piece of metal that sits there. That's the port that has a hole in it. The gas goes through it, but the port itself is not the thing that's flowing through it. And that's SysML's interpretation. So you'll see these things which are structural, and you'll see these things which tell you what's flowing through it. So to extend SysML, what we did is say, okay, well, this is good. I mean, it tells us the kind of thing that's flowing in and out. We know that when the system is functioning, the value of this property will be a quantum of energy or an electron or whatever it is that's flowing. But we need this other information that the simulators are concerned with, namely, what's the potential and what is the flow rate? And so we basically extended SysML by making a new kind of property that refers to this flow property, but then points off to what we call a sim block or simulation block that has all these variables that are identified as being either conserved, which are the flow rates, or not conserved, like this one, which are the potential. And we actually had discussions with some of the folks at OMG about exactly how to factor this, and we ended up back here because we need actually a block, which is something that specifies something that's happening in the operating system. So when the system's actually operating, there are instances here that will have values for these properties that give you, say, the voltage and the current, or whatever it is in your domain. So it looks a little bit indirect, but it turned out we tried less indirection, and it didn't really work very well. But this captures everything we need to say. So if you know UMLEs, you could read this. If you don't, basically, we take something from UML, like a property, and we extend it. We have simulation properties and variables and the blocks. And then you arrange that you point back at the flow properties, and then the blocks all have these simulation variables that are either conserved or non-conserved, that is, their flow rates or their potentials. And then there's other properties that are useful to simulators, like it's helpful to know if the value is going to be continuous. It helps if it's discrete to know if it's going to change at regular intervals, and so on. So these rules here, which I won't really read to you, are the constraints that happen in this extension due to those pictures I showed earlier. You know, you can't have unidirectional flows that are merging, and so on. That's what those are. I think I won't go through all of these, but there's a number of constraints that are typical in simulation tools, and we laid them out on the extension. So why don't we just go to the example. So this is an electric circuit, and this would be a typical domain picture like you might see in the simulation tool. And this is an internal block diagram in SysML. And SysML and also simulation languages only allow their connections between the components to be binary. So here you see n-ary connections. Those have to be broken out into binaries. And you have to do that with the simulation languages also. So you see that ternary up there is actually 2 binaries. And then these components, what you're looking at here in an internal block diagram is basically the type of thing that it plays this role. When you look at a block definition diagram, you'll see these rectangles, and they mean classes of things like cars and wheels and so on. When you see these rectangles in the internal block diagram, they're roles. So the name of this role is S, and this type is source, meaning that something of this kind plays that role. And it's the same with the ports. The ports have names, and there's something of this kind, a pin, that plays that role. And you see that these are binaries, so they have a P role and an N role. They don't actually call them roles. I call them that because it's easier to understand. Then if you look at the extension, you say, OK, well, this is an abstract block that captures the 2 pin components that we saw. You have the P role and the N role and their types. They're the ports. These are the sim variables that go on these components. You want to know what the current is going through the component and the voltage drop across it. And similarly with the pin, you're flowing, this is in-out, meaning it's bidirectional. You have electricity flowing in and out. It's referred to by this sim block, which has the current and voltage, and the current is conserved and the voltage is not. And when you break that down into the different kinds, the resistor, capacitor, inductor, the different kinds of components, you add other information about the constants like the capacitance and so on. And then these constraints, I'm going to show you, they're the ones that express the various laws like Ohm's law and so on. So this is what you saw in the previous slide. You saw your components, general component, the resistor in particular. And this is what's called a parametric diagram. And what these lines are is they tell you they're basically equality. So you can think of them as setting up an equation. So this is saying on the resistor, the V drop, the I through, which are the voltage drop and the current through the resistor and its resistance, are bound to these variables inside this constraint, which, as I'll show you here, includes Ohm's law. So here are the actual constraints. And they're modeled in a block diagram. The constraints are blocks in SysML. They have parameters, which are basically all the things that the constraint is applied to. These are the specific equations for the constraints. There's Ohm's law right there, and there's other laws for the other components. So that is, what I just showed you is a complete model of that original electric circuit. And then from here, you can start to transform up to the simulation formats. And I'm not sure I'll go through all of this, but this was the hardest part in some ways of what Ian did, because Ian and I did, because we were mapping across these different linguistic communities that were using overlapping terms. For example, in Simulink, a port means it has only one particular numeric value, whereas ports in Modelica and SysML can have multiple numeric values. So the purpose in part our purpose of creating the abstraction was we had to create an abstraction which isn't intended to be a language necessarily that people fall into, but when they're using SysML, they can think in this abstract terms and translate it to the others. So in Modelica, this is outputting a Modelica file. You see the type of the component is here, its role name is here, and then the values, those constants you saw are over here. And then these connectors, which also have to be binary, are referred to the component dot the port name. So this you can think of as a textual format for this. And in fact, SysML does have a textual format. If you look at it, it's not as compact as that. It's XML, but it says a very similar thing. And Simscape, almost identical. Simscape is basically Simulink's answer to Modelica, because Simulink is actually for the unidirectional flows, not for the physical systems. So they have this add-on module called Simscape, which basically gives you a similarly simple way to show these physical systems. Just a very slightly different textual syntax, which the translator can account for. So this one is mapping these constraints into Modelica. You have a resistor, and you see the ports, the pins of type pin, and it tells you this is its marker for conserved. And when it doesn't have that, it's non-conserved. So this one's voltage, that one's current. And then these equations are generated by taking these equations, and where you see the equality here, you replace the variable. So you basically can generate these equations from these bindings and the equations on the constraint. SimScape is also very similar. Its types actually come from a foundation library, which we couldn't actually, it's proprietary, we couldn't get access to it. But it has a very similar notation where it shows the variables. And then it has a shorthand way. Actually, you don't need to write it with using these keywords, but they're shorthands for the equations that you saw earlier. And then their equations have double equal signs. And all that can be taken into account by the translator. In Modelica, they have the notion of this sim block actually goes to what in Modelica is called a connector. It's the type that you can use to type your ports. So when you saw that p:pin, that means p, the value of p is of that type. And then the variables translate, as I said, the conserved go to the flow keyword. And like I said, we couldn't find these. These are buried in the libraries of SimScape. They're proprietary. So actually, Ian and I just, this was the end of these slides, but Ian and I just finished a paper where we had a signal processing example, if you want me to show it.
Yeah.
Okay, let me just track it down. Why don't I just show you the, I'll just show you the figures. This might be too small. Yeah, that's probably too small.
So when you simulate, what do you do?
Well, basically those.
Set that up now, okay, fine.
So those files then go into the simulator, and you probably need additional.
Where do you start the commands from? Simulate. Is it open loop? Do you do it runtime? No, runtime. To see what's happening.
Well, those once I think you need also the initial conditions, and then when you those files are in the format that they expect, so they're basically the model that's input.
I'm the user. I'm sitting where to simulate, let's say, let's take your example, the electrical network.
Well, those files then, when they're generated from the extension, would be sitting on your file system. You also need, I guess, to give initial conditions.
How do you use SysML to represent the initial condition? Like a boundary condition?
Actually, SysML has a way to present initial condition. For variable, yes, you can. There is a special section called initial. If you look at the properties,
That's okay, but
the value type, you do it from outside, basically. At least at this point.
problem number one. Problem number two. If I want to use this for design, okay, how do I do the simplest possible? I have an optimization criteria, and I want to change the parameters of the simulation to find which one is the good one. How do I do that?